Welcome to the Science Cafe. This is the spring semester, and we have, I think, 5 science cafes for you guys and a couple of cafe conversations. But before we talk about any of those, I want to remind all of the students and the faculty in the room that the Student Expo, the Research and Creativity Expo, is now open for submissions. The expo itself is on Thursday, April 9th. So as a student, if you have research, any kind of creative activity, something that you could present, this is a great opportunity either for your first presentation in a really friendly atmosphere or for your 20th presentation to get some more experience and to show everybody the kind of research that goes on at OU. So I hope that everybody will participate. Anybody signed up yet? Oh, we have a couple. Yay! All right.
There will be a cut-off this year. When we hit 800, we are done.
Did you get that? When we hit 800, I know you're thinking 800, that's a big number. No, it's not. Trust me, they'll hit 800 for this. So get in early or you won't get a slot at all.
826.
Last year were 826, even though they threatened a cutoff. Okay. So the other thing to note is Sigma Xi. For those of you that are faculty members, please think about nominating your students. Or if you're a faculty member and currently not a member of Sigma Xi but would like to be, you just got to talk to me. We need to nominate members. The annual membership drive is coming up. And for those students who are either nominated to Sigma Xi or Sigma Xi members, there will be a special judging at the science fair for those students to win prizes through Sigma Xi. Okay? Now, the last 2 pieces of events. The future, in 2 weeks, David Rosenthal will be here. He's from my home department, Environmental and Plant Biology. He'll be talking about ecophysiology and how trees relate global warming types of things. We'll have a title, obviously, out for you guys pretty soon. And then on February 11th will be the first cafe conversation of the spring semester, which will be Chester Puck of History. So things to look forward to, but right now, everybody is looking forward to Carl Brune from Physics and Astronomy.
So, good afternoon / evening, everybody. I'd like to welcome you to the Science Cafe, and I'm going to be talking about cosmic cooking, which what I really mean is the origin of the elements. And so, to get the conversation kicked off here today, I'd like to ask a question which is basic to the title, and that is, what is an element? And
Physicists, you're over there, answer.
somebody needs to answer this. We have chemists in the room, too. We have a... Am I the moderator for the questions as well? Over here, over here. Yes, please. So a basic unit of matter. I'd say that's a very good answer. And the chemical elements, the elements are the fundamental building blocks of matter, and it's what everything in this room is built up of. And as you scale up, you go elements, molecules, collections of molecules, and that makes the solids and the liquids and the gases. And as I said, essentially everything that's in this room here. Now, if we break down the element, which is what I'm going to do in a little bit, we'll get into the nucleus and the electrons. However, before I do that, I have a cute little movie which I want to show here. About, surprise, surprise, the elements.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
So there are the elements. There's quite a number of them. 192 gets you up to uranium, and now we've even gone farther than uranium. And so my question is, for us to ponder here today is, where did these elements come from, and where do we think they came from at least, and what are some of the open questions in the origin of the elements? And so, as I said, that's and what I want to provide you with, which is kind of a backdrop, a bigger picture of what we think is going on as far as the history of the universe. And so the elements are part of the universe, and that should fit into this picture of the universe. And what many people believe happened is that we have a beginning where there was a big bang in the universe, and the material was all very hot and very dense, and then it expanded and cooled, and various things happened over time. And part of what happened was that a few elements perhaps were created in the very beginning. Further processing has happened, which I'm going to get into, which somehow led us to where we are today, which is thought to be something like 13 billion years after the beginning in the Big Bang. And so what might have happened over this time to get us where we are today, where we have this great variety of elements. So a potential clue as to where the elements came from comes from looking out into the stars. And what one sees is lots of stars, but lots of other things. And this is a little bit of perhaps washed out with the light, but it's a recent Hubble Space Telescope image that's quite beautiful. It's not simply just some stars, but it's got these gas clouds, and the gas clouds are glowing. And the interpretation is that this is a star-forming region, which means that you have a large cloud of gas, and due to its own gravity, this gas collapses down and condenses into stars. So stars form, and it tends to be a very active region with lots of intense bright stars, massive stars, and that intense light, in particular ultraviolet light, is making the gas glow as it's ionized, and it gives rise to this very beautiful picture. And if by any chance you were paying attention to science news over the past month, this image on the right was just released, and it's a rather striking image, and it's interesting because this was first photographed by Hubble back in 1995, so quite some time ago, and it was decided to revisit it to see if anything had changed, and just also because it's so cool to look at. And sometimes you just have to not make it too complicated. It's cool to look at. And it's there. They've actually photographed it in more detail, and if you compare them, there are actually small changes in the plumes and things that have happened in the 20 years approximately that have taken place. And so this is just it's mostly going to be hydrogen and helium with traces of heavier elements in it. And this is just looking at the recent image again here. It's just a very beautiful and very striking image. And so maybe this is a clue as to where the elements came from. So I'd like to ask another element question. And that is, what is the most abundant element on Earth? And I'm thinking here maybe the most abundant thing should be the most important to understand and perhaps the easiest to understand. So what's the most abundant element on Earth? I can go back here. Nitrogen is unfortunately not the correct answer. I will go, excuse me? Hydrogen also is not the most abundant element on Earth. Let's go here. Carbon. It's a trick question, and you're getting at the trick here. Let's go way back in the corner. Iron. Iron is the correct answer, and it kind of depends on, did I say most abundant element on Earth or in Earth? Okay, and so it's the crust versus core thing. And it turns out that if you consider the whole Earth, iron is by far the most abundant element, and that's because the core, which is most of the Earth, is mostly iron. Now, the crust, just in case you are wondering, is the dominant element is oxygen, but also silicon is very important. So dirt and rocks are mostly made of silicon and oxygen. Iron is an important thing. Hydrogen is significant also. It's in the water. And there are good numbers of lots of other elements. And in fact, all of the elements except for technetium naturally occur at some level on the Earth. But iron is actually the most abundant. And that is another clue as to where the elements came from. And this gets to nuclear physics, because I actually am a nuclear physicist. I am not an astronomer. But it has to do with the nuclear physics. And the nuclear physics has to do with the nucleus, which connects to the elements. And so our elements in their stable, non-ionized form consist of a nucleus, which is positively charged, along with an electron cloud around it, which is what makes the atom neutral. If I want to drill down and see what a nucleus looks like, it's going to be a collection of particles of neutrons and protons. And so let's just imagine that the blue balls are protons and the reds are neutrons. A nucleus, something like oxygen, might look like this. Oxygen, the most abundant isotope is oxygen-16, would be 8 neutrons and 8 protons. And then you have your cloud of electrons around this. And so I study these nuclei. Maybe we should understand how big they are. This is a model which we can all see, but the real nucleus is much smaller. And how much smaller? Well, we measure the nucleus in units of femtometers. And femto is a 10 to the negative 15. Thank you very much, sir. And so that means 10 times 10 times 10, 15 times smaller than 1. And so it's incredibly small. Even an atom is large compared to a nucleus. And so it's almost like a point inside the atom, but they do have some size, but it's very, 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 very small. So iron, it turns out, getting back to the elements in the nuclear physics, turns out that iron is the most stable way to put neutrons and protons together. And if you start removing neutrons and protons, it's less stable. If you start adding more, it's less stable. And so if you have neutrons and protons, which is what the universe is mostly made of, it wants to be iron. That's its most stable state. And maybe that's a clue as to why we have so much iron in the Earth. Okay, let's talk about other abundant elements. So we've discussed the Earth. What about the most abundant element in the solar system? Any ideas what that might be? So this is now considering the sun, the Earth, and the other planets right here. So hydrogen is suggested and is the correct answer. Yay. And number 2 on the abundance list is helium. And that it really is the vast majority of what the solar system is made of, because the sun is so massive, it's by many orders of magnitude the largest mass in the solar system. It turns out by mass, it's about 3/4 hydrogen, 1/4 helium. And then there are just traces of things like what Earth is made of, like iron. So even though iron is the big winner on Earth, and now how did stuff get mixed up? That really gets into chemistry and geology, and when the solar system formed, it turns out that the gravity of Earth, for example, does not hold hydrogen and helium. So only the heavy stuff is left on Earth. But that's another clue, is that hydrogen and helium are very abundant. And it actually holds true if you look out at the stars, like in this picture, which I was showing before. Hydrogen and helium are the dominant elements in the universe. And things like iron, even though it's the most stable, are just tracers. So that's another hint as to where things come from. Maybe it has to do with nuclear physics. And there are a lot more hints along those lines, I will add, which can be very quantitative. And I'm just going to give you a flavor for some of these hints. And it has to do with looking at these heavier elements beyond iron. And if you look at the probability for capturing an extra neutron, it turns out that the nuclei which have a large probability for capturing an extra neutron tend to be less abundant, and the ones that have a small probability for capturing an extra neutron tend to be more abundant. And so there's this correlation with the abundance of isotopes or elements with their likelihood of capturing a neutron, which seems like a hint that maybe some kind of nuclear physics is responsible for what's going on there. And I want to develop that idea a little further. And so here is a picture of how we believe that the history of the universe is gone. So we had this Big Bang in the beginning, which produced, it turns out, hydrogen and helium, and I'm not going to go into the details of why we think that's the case, but only the light elements, hydrogen and helium, essentially with very small traces, perhaps, of lithium, also produced. That material would form the first generation of stars. The stars have a life cycle. So like even our sun, unfortunately, is not going to shine forever. And the stars also owe their existence to their shining to nuclear physics, and that's the energy source of stars, is the burning of nuclear fuel. It's a nuclear fusion reactor, essentially. That can't go on forever. They burn all their fuel. They either fizzle out and die when they're done, but some stars, the more massive stars, actually explode. and do a supernova explosion, which is a rare but very violent event. And so the picture here is that you have a supernova which explodes and blows out into the universe whatever nuclei it's got in it, including the ones that it might have produced, and then that can go into the next generation of star formation. And our belief is that the universe is over 13 billion years old, but the solar system where we are, the formation of our solar system happened only about 4.5 billion years ago. So there was plenty of time for lots of stars to explode and enrich the universe with with nuclei before we came along. Okay, so how do we go about understanding this in more details? And the research into this occurs on many fronts, and one is on astronomy and astrophysics. So making observations of other stars, seeing what the elemental abundances are. Maybe that gives you some clues as to what you see. Another very compelling fact is that if you look in other stars, which you see the same patterns of abundances of high iron abundance and low abundance of other things that you see on Earth. And that also is very compelling evidence that there is at least a common origin for the elements in other stars as well as what we see on Earth. And so the hope is that you could understand this in some kind of a unified way. So astrophysics and astronomical observations are a key component of unlocking what's going on here. And in particular, looking at the elements that occur in other stars. The solar system, our own situation, is pretty well studied. We think we know, but this actually is not always so simple, because even how do you know what's inside the Earth? I mean, that takes some pretty deep understanding of geology, for example, to figure out really what's going on inside the Earth, and I'm sure there are uncertainties there. So there's geology, there is astrophysics, there is also the modeling of stars and supernovae. And so this is people who try to describe on a computer how a star evolves over its life, what elements it creates, how it explodes. And then you also need nuclear physics, which is what I do, to try to understand these processes that create one element from another element. So this whole concept of cosmic cooking. So here's another question for the audience. What is alchemy? We could go right here. So it's changing one element to another, and this is something that, you know, back in medieval times, I think people had this hope that, you know, lead was heavy and gold was heavy, and gold was really valuable and lead not so much, that maybe if you did the right, you know, cooking on your lead, you could turn it into gold. And I don't think that ever quite worked out. And once, you know, chemistry, you know, evolved as a scientific understanding of the elements, and the elements were pretty fundamental building blocks, I think that pretty much sunk alchemy as a science. But maybe if we understand nuclear physics, and that came along not so much later, maybe it's not such a crazy idea after all that you could, you know, change one element into another. And it might be tough to get gold out of lead, but it certainly is possible. And I might even give some ideas about how to do that. However, I don't think it could be done on an economically viable basis, unfortunately. That's not so easy. So our picture of where the elements came from, to kind of answer the question in broad terms, is that hydrogen and helium, we believe, came from the Big Bang. They get cooked in stars. Some of those stars explode and blow their stuff out into the universe. And then that stuff forms new generation of stars, including our solar system as Exhibit A, which has elemental abundances which reflect what happened in the future. Now that's kind of a broad overview. What we'd really like to do scientifically is fill in some of the details here about exactly how did this go, and it's very complicated. There's a lot of elements, around 100 of them, and they all have their unique story to tell and get into some very interesting little details. So I want to get now into experimental nuclear physics a little bit. So I'm kind of going from the astronomy to something entirely different. And I want to say a few words about the laboratory that we have here at Ohio University on campus. In fact, just down the kind of across from Baker Center, I think we're right here. So just right over here, the Edwards Accelerator Laboratory, which is located kind of between Gordy and Clippinger. And we do experiments in the laboratory to measure rates of nuclear processes, which can then be fed into a model calculation of what a star might do in terms of making elements. And so that's where the laboratory is located, and this is what the accelerator in the laboratory looks like. It's a big orange tank, and it accelerates nuclei up to high speeds, up to about 10% of the speed of light. And that speed, roughly speaking, corresponds to what you would find in the core of a star, where it's extremely hot and the nuclei are moving around very, very fast. And the organizers of the Science Cafe did not permit me to bring my accelerator, it's not my accelerator, bring the accelerator to the Science Cafe today, unfortunately. It's actually too big and it couldn't be moved, but I did bring a demonstration accelerator, and so maybe we can move the table a little bit here. And this is just a graphical way of showing to some degree what we are doing in the accelerator, colliding nuclei together and measuring what happens. And so this is a little bit of a leap of faith here. My nucleus is not going to go anywhere near the speed of light, and this is much larger than a real nucleus, and we're not really going to detect anything, but we're going to see what happens. And maybe this is a good time to talk about an important point about the nucleus. So I said it was neutrons and protons. What is the charge of a nucleus? What is the sign of the charge of a nucleus? Got to raise our hands, son. Yes. It's a positive charge. Now, if my other nucleus is kind of locked in place there, but if I have two positive charges and I try to bring them together, what happens? They repel. So like charges repel each other, and this is what prevents nuclear reactions from happening kind of in our daily lives. If you are of my age, you may remember cold fusion or greater. And this was a scientific claim in the late 1980s that if you put put heavy water, which is deuterium-containing water, in palladium in the right way, and I don't know, cross your fingers, that you would actually get get energy coming out from fusion reactions in this contraption. And it's very compelling because heavy water, deuterium, it has a lot of potential energy, and it's certainly energetically favorable to fuse deuterium nuclei together, and you can get energy out. It's similar to what happens in the core of the sun. However, there's this problem of the positive charges not wanting to get ever close together, and at room temperature, that is, say in this room, it just doesn't happen. That the deuterium nuclei kind of get, in the neighborhood, and then they go, ugh, and they push themselves apart, and nothing happens. And in order to get fusion to happen with a useful rate, you really need to get billions of degrees. Okay, so it's like way beyond any terrestrial temperature. It can be done actually in the laboratory with plasma physics techniques and intense lasers, but it's extremely, extremely difficult, and it's not going to happen in a tabletop laboratory experiment. To the best of our knowledge, maybe somebody will figure out a way to overcome what we call this Coulomb barrier. But what you can do, if the speed is high enough, it can happen. And that's why you need to be in, say, the core of a star or something, and why you would need an accelerator to do it. And so this is my mock-up accelerator where we use the gravity to accelerate a nucleus and collide them. And let's just try it and see what happens. And remember, the chemical element, if this is reds are neutrons and blues are protons, the chemical element is defined by the number of blue balls. You count the number up, and that's the atomic number. And these are, by the way, held together with a magnet in the core, so it's a little bit contrived as well. But let's just try it. I'll start with a lower energy first, just because didn't do anything. Better raise the energy. Well, these are some tough elements here. Let's get some. Well, let's go on. There we go. So if you collide these things together enough times and hard enough, you can change the element. And you notice we've removed, in this case, three protons. And so this definitely made a different element. Let's put it back together again. Most of the reactions which happen inside stars which create elements are actually a little bit different from the picture here. Maybe not quite as dramatic, but it's more like the following. You have a heavier nucleus and a single neutron or a single proton that comes in and is captured, which makes a heavier nucleus. That would be actually a more common scenario for how you would build up a heavier element. Anyway, there's a tremendous number of possibilities for nuclear reactions, and this is conceptually how we study them in the laboratory. We collide the nuclei together, we detect what happens, we see what nuclei we made, and use nuclear physics to understand what happens inside of a star. Another thing that's very important that happens when you fuse light elements, you not only make new elements, but you create energy. And that's why our sun is shining, because it's continuously fusing protons together to make energy. So that's what we can show with the accelerator. This is a picture of the accelerator at Ohio University. We use this to study to study nuclear reactions, and it's conceptually very similar here. So when we move the table back to its old setup here. And I want to show now another little movie which is showing, I'm going to probably repeat it 2 or 3 times, and it's going to take me a little while to explain what's going on. This chart is a table of the nuclei. Now, you may be familiar with the periodic table of the elements. That was the element song in the beginning with 1 square for each element. This table breaks things down in a little bit different way, where we have the number of protons in the nucleus on this axis and the number of neutrons on this axis. And this is because the number of neutrons and protons are roughly equally important. And this is a movie of a calculation done by these scientists. And what it's showing is something called the rapid neutron capture process, which is how we think the elements heavier than iron were formed. And it's by capturing neutrons in some environment, and these neutrons build up the heavier elements. So let me play this again. And what you want to think about is neutrons horizontal, protons vertical. The black squares, by the way, are the known stable elements, and so these are our standard elements along here. And this shows the cooking that let's do that. It shows the cooking that goes on, and so the neutrons cause very quickly the production of heavier elements, and then this is showing the temperature here. It slowly cools off, and these elements slowly evolve their way back towards being the stable elements. And so eventually they're going to do that because of their half-life. And this is the model where we think most of the heavier elements, such as uranium, were formed somewhere. And this rapid neutron capture process is actually one part of this puzzle that we're not very certain of. And here's the thing. It's known to take a large number of neutrons to make this happen. And if you put the large number of neutrons into your calculation, you sort of get the right answer as far as what we see on Earth. But nobody has any idea for sure where this happened. And so there are competing theories out there, one of which is coalescing neutron stars. And so, this is another science cafe that's happened in the past, is neutron stars. Well, if you have 2 of them, they could coalesce, and some of the material might be ejected out, which could explain what happened here. Another idea that people have is supernovae, but although people have very good models for supernovae, it turns out when you do the calculation, it doesn't work. And so there are competing ideas as far as what the explanation for exactly where these heavy elements are coming from is. And so this is something I think to look forward to. There are also major nuclear physics uncertainties in this whole calculation because, as you saw, a lot of the cooking was going out here very far away from our known stable elements. And that is experimental nuclear physics, which has not yet been tested, not been measured in the laboratory. And so we also don't know a lot of the basic input physics to understand what happens there. Yes? The color code is abundance. And so now how, with the reds being the most abundant, the yellows being next, green, and then blue. So maybe we should try this one more time. So think about the reds as being the most common and the blues as being the least common. And another thing that's striking is that there are certain regions where the red accumulates, where the most abundance accumulates. And this is related to nuclear physics also. It's something called shell closures, and it's like the shells in an atom. There are also shells in a nucleus. In fact, there was a Science Cafe talk on this probably 4 or 5 years ago. Jolie Krzyzewski spoke about this, and there are certain magic numbers where you actually get more abundance, and this matches actually what you see in the solar system, that these certain regions of atomic mass are more common than others. And so that's one feature which is trying to be explained here. Yes? So I would say that the division between physics and chemistry is somewhat blurry, and the study of elements and isotopes has part of that happens within chemistry. So we don't so much have that at Ohio University, but nuclear chemistry is a discipline of chemistry which is concerned with, historically especially, with new elements. And so I would say there most definitely is a role for chemistry in understanding this. Any other questions? Well, we're on the question theme here. And so as a nuclear physicist, I'd like to understand, and as a nuclear physics community, we would like to understand some of these questions better. And to get a better understanding of the nuclear physics, I want to, and this is, I'll just say briefly, this is that same chart, and maybe I should have shown this one first, that shows, again, the elements, but as the function neutron number, proton number, and this is the same plot that was shown in the movie, and this red area was where this rapid neutron capture was happening. What is being done to address the nuclear physics in the United States is the construction of a new laboratory. This is a national laboratory for the study of nuclear physics with these very far off the stability nuclei, and it's something that's called the Facility for Rare Isotope Beams. It is under construction at the moment at Michigan State University, and it's a very large-scale thing. This is these are already very large office buildings over here on the MSU campus. The cost is approximately $500 million. It's being shared by the state of Michigan and the U.S. Department of Energy, and it involves a fairly high energy heavy ion accelerator, which is going to accelerate a nucleus like uranium or lead or whatever, crash it into a target very much like what I showed here, and make some other nucleus, but then it's going to separate that other nucleus out, possibly reaccelerate it, and then do more experiments with that radioactive nucleus. So it's a very large-scale, very complicated thing to enable the study of these rare nuclei very far off the line of stability. And this is something, it's going to be another decade probably before it's fully functional, but construction is already begun, and a large motivation for undertaking this is to understand this so-called R process, rapid neutron capture process, and at least from the nuclear physics point of view, figure out what's going on and what's going to govern the rates of these reactions. So I think I'm going to wrap up my presentation at this point and just conclude with a quote from, very simple quote from Carl Sagan, that we are all made of star stuff. At least we believe that that is the case. And hopefully I've given you some insight into why we think that. Anybody have questions? So the question is what happened before the Big Bang, and and possibly whether or not that is a scientific question. And I think that it is a natural question to ask, and it could be a scientific question. The problem is, as I see it, with when you try to go back in time with the Big Bang, you get to higher extremes of temperature and density in our understanding of physics. And the farther back you go, the more uncertain things get. And then to even go beyond that, to say before, I personally just can't have much confidence in answering that. So maybe that helps or maybe not. Yeah. Probably not. And it would seem, at least in the most straightforward implementations of the Big Bang, that any memory of what happened earlier is effectively lost. So if there was a, excuse me? I'm not. Yes. So we can study certain things on any elements. The thing to do with the size has to do with what this is buying you, it turns out, is the ability to get far away from the line of stability. So you may be, I don't know what your science background is, but there are stable elements that have a certain numbers of neutrons and protons, and it's easy to go 1 or 2 neutrons or protons away from this line of stability, but it becomes harder and harder, energetically unfavorable, to go 10 or 20 units, which is what this facility can do. And so that high energy fragmentation mechanism, which is basically slamming two things together at a high speed, it turns out with reasonable probability will make these far off the stability line isotopes. Sorry. Do people from other universities come here to use your accelerator? And the answer to that is yes. We have actually quite a large number of outside users from national laboratories in the United States, in particular Lawrence Livermore and Los Alamos National Lab. Also, the University of Oslo, that's in Norway. We have had outside users recently from University of Michigan. SUNY Geneseo is another one that comes to mind. I should also mention that our accelerator is used for a number of things besides this astrophysics. Okay, so it's not just this, but we do applications of nuclear physics. We also do basic nuclear physics, nuclear structure studies. What are some of the applications? Not the subject of today's Science Cafe, but one of my favorite examples is neutron imaging. And so many of you would be familiar with using X-rays to say, if you go to an airport and you go through, put your stuff through the scanner, that's great. It doesn't, if you have, a gun with some metal in it, hopefully you don't, but if you did, it would show up on the X-ray machine probably. But other things might not. For example, a plastic explosive is not detectable by X-rays because the constituents, the carbons, the nitrogens, the oxygens, and the hydrogens, they're just too low atomic number, too low a Z for an X-ray to differentiate it from, like fruitcake or something. So it's a challenge for airports, and that's why they try to do like swipes and something like that. But neutron imaging, in principle, would be perfect for luggage screening in airports to look for explosives, for example, because neutrons are neutral penetrating particles for nuclear physics, and so it would be my my neutron, and it turns out neutrons have a very large cross-section for interacting with these light elements that I mentioned, the nitrogens and oxygens and hydrogens. And you can get beautiful images with neutrons. And this is something that's been developed in our laboratory. And if the will is there to implement it, this could be implemented in airports to look for explosives. That's one application. There are with other accelerators, medical applications. There are making isotopes, for example, for PET scans and various radioactive tracers. There are other applications for national security, for example, to look at detecting uranium and the non-proliferation. There's the study of materials, so figuring out what an unknown sample is made of and what the composition, thickness of layers, and things like that is. So that's some examples of applications.